Hello everybody again. Last installment for today. We're going to have a presentation from Luis about evaluating model predictions, and especially when those models are intended to be risk maps. So this will round out today. I have to say I'm very happy with how we are doing with this online format in terms of getting content out and having people tune in from Mexico and New York and Arizona. But what we are not getting is interaction. So if you're out there and watching, send us some questions. It's really hard just to talk to a screen. So send some questions and we will attend to those first thing tomorrow morning, but do send them. So for the moment, I'll leave you in Luis's hands with a presentation on testing your models.
Thank you, Town. Hi, everyone, and thanks to be here. Sorry, but it's me again. This one. But something good that is that this topic is really amazing and is critical when modeling diseases. I'm going to talk about evaluating maps. So the question is our map robust? Is correct our interpretation? So I would like to cite Peterson 2014 that says that adequate models evaluation is a sine qua non for model interpretation. So this you must do it if you are going to publish mapping showing diseases. This is the second part of the presentation of Town about ecological niche modeling overview of process, and I'm going to give some details about this part of model evaluation that is the final part of the process. So I would like to ask you, once you are ready to publish your map, if you are sure that you can put your hands into the fire for your prediction. So there are some ways in which we can answer yes to this question. First, how can we measure the quality of the prediction of our disease maps? First, these are the steps. We are going to follow them. First, choosing evaluation points, then evaluation areas that are really close in the practice, and then identify which kind of output we are going to manage, and identify the algorithm to run the evaluation, and finally, a single slide of interpreting results. So let's talk about evaluation points. And the idea is that we must have external points. It is points that are independent and that were not used for model calibration. So this should be independent data for sure. And for example, here is a study area in one part of South America, and let's imagine that this was the study area of the process, and that this is going to be one small area that I'm going to consider for this example. So I have one point that was used for model calibration here and was collected by other authors and other researchers, and I used it to calibrate my model. But I have this other point that I collect by myself. I'm sure that this is a very robust point of disease occurrence, so I'm going to use it as evaluation point. So apparently we might think that these two points are independent. But if we go to the ground, we can see that the landscape and the geographic distance, maybe the environmental and climate factor related, are very close between these points. So even when they could be collected by different group of people or in different places, they are not independent data. So if the question is if they are independent, no, because there are a level of autocorrelation here. And if we use the red point to calibrate the model, and then we use the blue point to evaluate the model, we are not using independent data. We are evaluating the model with the same geographic position or environmental position. We are using the same points for calibration and evaluation. So what to do if I do not have external data to evaluate my model? What usually we have been using is split the data. So what we do is that we select a set of points for model calibration and then another set for evaluation, and usually this split of occurrence points is done we do it in the total amount of occurrence points available to us. Once we have the evaluation points, we usually extract the value to point in the GIS softwares to know the value of the prediction under each point. So maybe this is not very clear, so I'm going to show some diagrams for this. Let's imagine that this circle, this white circle, is one study area. These are all the occurrence points that I have available for my diseases or my vector. And I'm going to split this study area in 4 panels here to have diagonal areas of points. In this case, I'm going to use the A areas for calibrate the model and the B areas to evaluate the model. So this is an example of the configuration when we are going to split the data. This is a real example using backbone rabies in Colombia, rabies from bumping pads transmitted to people or to cattle. So all these points were collected in the field using GPSs, and what we did is that we split the data in the same configuration that I mentioned before. But something is happening here. We have some cluster of points, so that could add some overfitting to our model. So we must clean a bit these points, and what we did is that if the gray squares are the size of the pixel from the environmental variables, we are going to collect only 1 point from this environmental pixel. So let's see these green points. Those are the original points, and the red points are the new points, representing only one value for each pixel. So we are going to have only one environmental representation from that geographic position and not a lot for using original points. So we are going to have something like this that is going to be converted to something more like this. So if we have this example of configuration, we are going to calibrate the model using only the calibration points, and we are going to remove from the process the evaluation points. We are going to save them in another place, and then we have the product or the output of the model. We are going to release them into the map. But we could have another configuration like this one here that is a latitudinal configuration of the study area. This example is for Chile, and what we did is that we used for calibration the areas 1, 3, and 5, and then we evaluate our model with areas 2 and 4. So here we are trying to look for some kind of independence from the areas used to calibrate the models. So we do that to establish the occurrence points. Once we establish the occurrence points, we can cut the study areas to choose one for calibration and another for evaluation. This what I'm saying is that we are going to choose the evaluation areas, and then we are going to cut those evaluation areas, trying to look for areas that are not including points used for calibration, only points that we have saved and that we are going to use to test the model. We are going to do this only first for these areas, and then we are going to change the evaluation. The evaluation points are going to be for calibration, and the previous points used for calibration this time are going to be used for evaluation. So in this way, we are going to have two evaluations of the same model, the same variables, to see and to be sure that our model is robust. And in the other configuration example, we are going to have the calibration points in areas 1, 3, and 5, and we are going to have areas 2 and 4 to evaluation. So once we develop the model, we are going to cut only the evaluation areas, those areas that are without calibration points. So this has been developed previously to map infectious diseases. So in this example, the researchers developed a model using the blue points, and then they evaluate the model with the red points, and they use the same in the opposite configuration, using the red points to calibrate the model and then evaluating the model using the blue points. Once they are sure that the model is robust to predict the evaluation points, they can use all the points to generate the final model. And so they obtain something like this for the geographic distribution of monkeypox. So let's talk a bit about the output. We could have two kinds of outputs. The first one could be a continuous map from which we have continuous values from high values related to the presence of the species, and low values from which we do not have the environmental combination. Or the combination is too far from the observed values. But on the other hand, we have binary maps. So we have only two values, present or absent, or zeros and ones. And the terms are that presence represents the presence of suitable conditions, while absence represents the absence of suitable conditions in the area. So once we identify the kind of output that we have for our model, we need to choose the algorithm that we are going to use for model evaluation. And this is really hard currently in the field of ecological niche modeling, because we do not have a lot of tools to do it. I was impressed once I was involved in this field, because usually this point, the model evaluation, is not very strong when mapping biodiversity, but when mapping diseases, we must to be more careful. Okay, this is an example of one output in one evaluation area. So I cut the evaluation area previously. This was my prediction, and I'm using the points that I saved previously, and I'm plotting the points in the geography. So I can see that some points were predicted correctly, while there are other points that fail to be predicted. And there is another area predicted, but I do not have points that fall there. So let's see this example here. It's the same points, the same study area, and I have something like this. Here, the area predicted is very, very good to explain the distribution of my evaluation points. So I would like to know if this prediction is good enough. So I have another configuration of one output, and I have more area predicted. Here, one point was not predicted correctly, while here all the points were predicted correctly. This could be established as good models, but we need another step to do a p-value for this, while here I have a bad model because I have a few area that was predicted as present, and I have all my evaluation points that were not predicted correctly. So in this other example, I have all the area predicted and all the points were predicted correctly, but I cannot measure the good performance of the model under this configuration because it's not giving me information about a good prediction. Here are other examples of what can we find when modeling in the output areas using evaluation points. And for example, here, this is a good model that is predicting correctly all the occurrence points in a small area predicted, but maybe it could be interpreted as overfitting of the model around the observed values. But here in the right, we have another example in which 50% of the points were predicted incorrectly, and 50% of the area was predicted as present. So this model is not going to give me a better approach compared by the random prediction. While here we have the 50% of the area predicted, 90% of the points predicted correctly. So maybe this is going to be a good model. But here, finally, we have a bad model in which we have the 50% of the area predicted and only 10% of the points were predicted correctly. So we are going to have a lot of different areas, proportion of areas predicted and points, evaluation points predicted, and we must to give a measure of a statistical measure of effective correct prediction. So let's choose the software for the evaluation points and the algorithm for binary maps. This is the proportion of suitable area that was predicted. Here is more or less a 50%. That is the red area. Here we have all the trials that are all the points that I have to measure the model performance, and we have the points that were predicted correctly. So we need only this information to establish if the model is better than random. So what we do is that we can use, for example, Excel, and we establish the proportion of the area that was predicted suitable, the number of points used for the evaluation, and the points that were predicted correctly. So we use this algorithm that is the cumulative binomial probability -1 to have the p-value. So usually we are going to need to change the kind of cell to number because it's usually scientific. So that's the way to measure binary maps. But to continuous maps, there is another approach that has been using more commonly. This is an example of an output of a continuous map, and we are going to have one evaluation area that is going to look something like this, from which we have values of high suitability and low suitability, a lot of points across this area. So what I want to know is this: if this model is better than by chance. So what we must to learn is that there are two kinds of error. First is that error in which I have some points, some evaluation points that were not predicted or were predicted absent, and that's going to be the omission error. And then I'm going to have some areas that I know that the species is not there, but the model is going to predict that area as present, and that's going to be known as commission error. So this configuration is the confusion matrix. I guess that's a very good name for this matrix. So how to evaluate the errors in continuous maps? This is a very common tool used to evaluate this kind of models based on true absence, the proportion of true absences, and the proportion of true presences. But so we are using commission error and omission error. But this course, this configuration, which name is the area under the curve of the receiving operating characteristic, was first used during the Second War for the analysis of radar signals. So this was not developed for disease mapping, and currently is often used in medicine to evaluate the performance of some diagnostic tests to evaluate how well they can establish if there are some diagnostic tests that fail to predict the disease, and they can establish the best portion of this test to if they are looking for sensibility or specificity of the tests. So I would like to put a little bit of attention in this part of this test, that is the commission error. Because commission error is the areas that were predicted as present, but the species is not there. So that's not a big deal for some organisms. But on the other hand, we have the omission error, that is the area that was predicted as absence of the species, but we know that the species could be there. And these tools are using this information as if they have the same meaning or the same weight. So the issue is that this measure was used mainly. This measure was used mainly to model plant of birds. So if we are making a model of the areas predicted as absent for birds or for beautiful plants, there is not a huge problem if we are saying, no, the species is absent here, when in fact the species could be there. But when we are working with more perilous or dangerous organisms, we should take care more about these issues. So I would like to encourage to everyone to read this paper, because it discusses the issue of this measure when measuring the performance of ecological niche models. And you can see that this is a very weak measure, and this is dangerous if we are making maps to give public health efforts. So we are going to avoid this measure, and what we are going to do is that we are going to use a new version of this measure proposed by Peterson and colleagues, in which the commission error is not used anymore, and what we are going to use is the area, the proportion of the area predicted. The proportion of the area predicted presence. So we are going to work with the evaluation points and the area predicted present, because I have the knowledge for both of them. So what this measure does is that it's going to work with the level of error that I can support in my prediction. Sometimes I'm going to go to the field to collect the points, and I'm going to use very good diagnostic tests to identify my disease. So I'm going to establish a threshold of error that is going to be small. But sometimes I'm going to use some information that is second-hand information from my disease with variables that are not going to be good enough. So I'm going to provide or establish more error in my prediction. So this level of error is going to be in this axis and we are going to measure the area predicted only in that area. So this error is going to be established as a threshold to establish binary maps. So we are going to have a configuration like this one from a binary map, in which we are going to have a threshold of 0 error, including all the evaluation points, or we can have a 1% error, including 1% of the points outside, or 5% of error, or 10% of error. So these are going to be the areas that are going to be used as in this configuration of measure of error. So this is going to be the real prediction, the area that was predicted after using the threshold, and this line is going to show us the limit of null models. So we measure a radio between both areas that is going to look like this, in which we have the area predicted compared with the null model, and that radio is going to be our measure of model performance. So ratios that are going to be bigger than 1 means predictions that are better than the null model. So which softwares are available for this evaluation? Well, there is this Partial ROC software that is currently available, so you can read this manuscript that is providing more detailed information about how install the software and how to feed this software for a run one model evaluation. But briefly, what we need to do is extract the evaluation, using the evaluation points to extract the values in the continuous map and transform that information to a CSV file or text file, and then we need to convert the continuous map from decimal values to integer values. We can do that via multiplying for 1,000 or 10,000 and then converting the table of that raster file to a text file. So then we choose the error and we establish the output for the result, and we can generate the output. So in summary, you can follow these steps that is done on the software. Choose the right format to feed the software, establish the threshold, and choose the number of times in which you want to do that, because what it does is that you can choose a set of permutations without replacement to have to capture the variability in your prediction. So to interpret the results, you are going to have for the binary maps p-values that are very common in science, and in the other hand, you are going to have ratios that are very accepted in the field of niche modeling, and you can do different comparisons because in this way you are capturing variability between the models. So the future directions for ecological niche model evaluations are as follow. First, what is happening is that the current approaches are looking for a geographic configuration. So we are splitting the data according to the geography, and doing that we are having a lot of assumptions, because this configuration assumes that the landscape is homogeneous. But now what it has been proposed is that we can do this kind of a split of data and areas according to the environmental information. So let's imagine that we have this study area. These are the environments available in this study area. We have environment 1, environment 2, and these points, these gray points, are points are the environmental space or the background that is available in the study area. So we have the observed values or the occurrence points for our species or disease, and what we do is that we split the calibration points, and then we collect the evaluation points and we save them to run a model using only calibration points. So this can be done using the software, so I include here the link for the software that is a new tool to work ecological niches into the environmental space, but this kind of evaluation is something that is still in exploration. Finally, I would like to show you this book that is going to be released in November. So you can use this book to improve the small information that I provide here, because in the book you are going to find better examples and more detailed information of what I mentioned here. So that's all from me for model evaluation. I hope it was not so confused, and thank you for being here.
Okay, thank you, Luis. That was an overview of model evaluation, and everyone do be aware that without a model evaluation, a model has, I would say, no value. So this is an absolutely crucial step. Thanks a lot, Luis, and everybody. Will see you tomorrow. Tomorrow will be a lineup of modeling examples, essentially case studies of these methods. So we'll see you all tomorrow morning. For us, 9 a.m. London time 3 p.m., Nairobi time 5 p.m. Okay? Thanks for tuning in. Bye-bye.
Thanks. Bye-bye.